That's
SU2.
it. That's it.
You know, I realized that the front end that I'm running here is a 9 GB front end. Okay, so should I be looking at these
You
things
should
here?
go all the way to the bottom,
Okay.
or not maybe all the way to the bottom, but it's near the end of this. Actually, maybe we can start with let's start with that histogram. Actually, if you don't mind going down further. Yes, that one. So you had a question about this one, right? Remember this? So Nick has a lovely new histogram that actually breaks down these bars by the area of math. And
Okay.
so you can answer that question quite nicely. I think you just have to
Where
go
is it?
down. I think we were just working on it, so I think it's not even in the right place, but there it is. Yes, that's it.
Okay, but now we had some mega. Oh yeah, that's nice, and I think we should use this. But we had some bigger categories which had made up for the Euclid post, right?
What categories?
Well, I don't know. I have to look for them.
Metamath categories, you mean?
Yeah. I mean, there were categories. There were post. Hold on.
Yeah. And I think I've used those for the histogram.
Okay.
I mean, they are Metamath categories, so they should be there.
No, here they go. I mean, this was curated, right? To just say graph theory, linear algebra, etc., rather than these things here.
But we have
I mapped those.
We have graph.
No. I mapped these capital letter categories to things that were simpler and more, okay? That's what I'm saying.
Okay, well, we can do that here.
Okay, here we go. I got it right here.
Yep.
Vertex labels, this is the thing, okay? And then we vertex deleted that other stuff. So we can do exactly this here. Shall I run this right now? Should I run this?
Sure, why not? Yeah.
Okay, so where do I start from? Okay, so let me just look in this post. Okay, so we will have first introduced the color coding here. Am I making sense?
I believe so. I don't think it comes before that.
Okay, so this has color coding, and it has something that looks qualitatively like oh, those were color coded there. Okay, here we go. Step one, the dependency graph is, maybe I have to repeat that again. That's a pretty nice step one dependency graph. Okay, well, let's just see if this runs.
I hope it does. Yes. Okay, good.
Okay. Okay, so I think what we have to do here I think we should reorder these a little bit. And we should call these, okay, because we've classified these things previously. I see. What we should call them, let's see, where am I putting these? How the heck do I have these? I thought I had a formatting one of these. Really? 88 is formatting? Do I need a 92 formatting? Maybe I do. I just want a general file.
92.
Okay, so what I think we want is something here where instead of giving these, we say, and we're going to end up wanting to reorder these. I think we should say numbers, logic. Oh no, wait a minute. The first one was, wait a minute. First one was, yeah,
functions.
Can I join really quick? Because I have a delay of 10 seconds or something. I'm confused.
You want to rejoin?
Yeah, because your video is like delayed.
Okay, go for it. Yeah.
Yeah, no problem.
That's what we should do there. And we should reorder those. Now, I don't know how to put those in the right order, so we can just take we want that to be 2, 4, 3, 1.
Yeah, that's better.
Right. Okay, so then we're going to have that thing is going to end up having similar, you know, we'll deal with that as well, because that will be real, you know, that has these other categories.
Yes.
So we need to make sure we have the right categories here. Okay.
Can we say fields of math or areas of math? Categories means something else. And category theory is in there, so it's confusing.
Okay.
It's actually hard because field is something, area is technically something. It's actually a little.
Yeah, right. Okay. Let's run this now. How long does this take to run? We should save this graph distance matrix in a WDX file.
Okay, I'll make a note of that.
Well, as soon as it comes up here, let me just go ahead and save it.
Wow.
How do I say W? How long does it take to run?
Nick, do you remember how long it took for this to run before?
A minute or two.
It's taking longer than that on my machine.
like those M1 processes improved much on this.
Perhaps they
pipeline.
did. I mean, I have the great big top of the line Mac here. Up there we go. We ran, and now it's saving a WDX file, WXF file. Wow, that's a big puppy. Wow, this is really big. How big is it?
40,000 squared.
It's not dense, is it?
It's dense.
Oh God.
Also has infinities there. It's like symbolic.
Oh no, how big is that? 40,000 squared is 40 is 1.6 billion. This is going to be huge. Oh no.
It's gigabytes.
How many gigabytes, I wonder? You know, the front end that I'm running right now is at 9 gigabytes. Oh dear, what is going on here? This is, I mean, it seems worthwhile to save this.
Maybe in compressed form. Maybe compress it. Compress it first.
No, WXF does that.
Okay.
WXF is an efficient format, although it can be more efficient. You know, we could do dump save and put it in an MX file. That might be more efficient if it's
in this case, maybe like replace infinities with -1. Make a packed array.
Let's do this. Let's say dump save. That's just serializing out the pure raw data structure. Okay. So when this is done, okay, so we got to aggregate some of these things. And we've got a color code from the Euclid blog for all these things.
Right,
We've got naming for all these things. So let's use that, rename it a bit, and then we're going to put it in here.
Good.
Okay, so that's one thing we're doing. Okay. Now what's next that we can look at here? What's this?
We can look at this. This is a different version of the Pythagorean cloud. It was made, Nick, you made it using your new Metamath importer, right?
Now, hold on. Just a different approach. So instead of dependency, just a dependency graph, you just use an actual proof structure. And then essentially the same thing. Just covering is a little bit broken here.
What's that?
Just the covering is broken.
But wouldn't a dependency graph be more in line with the other stuff we have?
Maybe. Then you just don't have to change anything.
I think this is better. I mean, the coloring has to change.
Yeah.
But it's more readable. The other thing is we can relabel the vertices so that it's actually intelligible. So that's the other thing.
How can we relabel the vertices? What the heck are we going to put into them?
Well, we'll look up what they stand for, and we'll come up with some concise.
But there's a
Label
lot
for
of
each
them.
of
We're
them.
not going to do every one of them here.
I think it would take only a few minutes to do it for this. It
I
actually
don't
wouldn't be that hard. Look, we can
Try it.
just
Okay. All right. Oh,
I mean, we won't do it now, but I don't mind doing it. It'll just take a few minutes to look them up. If this is an important object.
Wait a second. Where is this? Did this finish?
Yeah, it's like now it's there 2.5 gigabytes in the Dropbox file.
It's not showing up in my Dropbox file. Did it go in? Oh, shoot. I put it in the main.
Yeah, not in the data.
No, but I put that's a WXF, which is not what I wanted. What I put there
Yeah.
was a set MM. Oh, their distance matrix 2.48. So I had both of them.
Yeah.
I had both. So I'm going to put them both. I messed up here. I put them both in the data subdirectory. Okay. It's a bit wasteful to have both of these giant files here. It's kind of interesting that they're so close in size. Really, it is kind of interesting. They're so close. Okay, there it is anyway. So, okay, so let's take a look at this thing here. How many reachable theorems from a given theorem are there? What does this have to do with anything? So this is okay. So here, let's look at what we've got. This. Okay, so here's where we reset those things. Okay.
Okay.
Metamath domain weights, Metamath. What is this? Base ID. So this is removing various things which we thought were not desirable. Okay, let's go here. And what is this now? This bar data, oh, we're still running this. So is this F rows going to be, okay, what's this? So is F rows, how long is F rows?
How many vertices there? 42,000.
35,000.
Why it's less?
Because it says except infinity. No?
But you're mapping them over the matrix of 42,000 dimensions.
Well, it's not 32,000 dimensions.
Oh, it's that old one.
Oh, for God's sake. Okay, where is the new Metamath graph?
It's the one we exported in the data folder.
Okay, so let me write that. Which one is it? Is it?
Well, actually, you can, I think, I just send you a mail that is relevant. You can just use it. A similar approach. Just for Norm-McGill's maximum, but you have to maybe use it for the setmm. I just want to cloud publish all these Metamath objects instead.
Okay, but not a multi-gigabyte one. That's not going to work well. I don't think we should.
If you compress it, it's like maybe 30 megabytes. Just
Okay,
the data.
Okay, so what do you want to do here? So you're going to push that. You're going to push the new Metamath, the new SetMM matrix, right?
Maybe it's easier to get like one in the new Metamath import. So in our function repository sources and not in the revisions folder.
Okay, I'm going to delete these two 2.5 gigabyte things because they're both wrong, right?
Yes.
Okay. All right. Now what? Now what are you saying here?
Then just in the revisions folder.
What do you
There's a
mean the
new
revisions folder? And
Metamath import file. It's like my new version. I just have the
so what do you mean by the revisions folder?
For the function repository sources. It's physics.
Okay, I get it.
It's notebook.
Revisions here.
Yeah.
Okay. Now what should I do here? Should I
It's
run
just,
it?
No, just take just copy paste from the neat example setMM object, that the iconized thing, and use it, or maybe save it in the data too. Or you can also run it. Yeah, why not?
Well, here it is, right? It's there. It's right there.
Yeah. If you like want to extract some graphs and properties, like Metamath graph would be just one property of this object.
Okay, what should I do here? Let's be very practical. What should I actually do? Should I save this, or should I just run this, or what should I do?
Let's start with running it.
Okay, so I got to run this file so that I've got the
Yes.
Metamath import.
Yep.
Okay, so here I'm going to run this.
Yep.
Why don't I copy it into my formatting thing?
Okay.
And let me call this Metamath graph. Oh, it isn't the graph yet.
No, it's an object. You should ask for a dependency graph. That would be a graph. Or something not properly. Hold on. You run all the initialization steps, right?
Yeah, I did the initialization.
I see there is a typo there. You name it stuff.
What happened?
Can you try it again?
Rerun the initialization.
The new version, because I updated something. One line.
Okay. Now, Metamath graph.
It's a dependency graph property.
Like this.
Yes.
Okay, so should I store this MetaMath object? Is that the right thing to do?
You
I
can.
should probably
Yeah.
store that. Okay, so let me say export to mmset object dot wxf comma %8, or actually
Is it exporting all the definitions? I wonder.
No, dump save would do that, but this doesn't.
Or maybe just dump save it and you don't have to run this notebook. Unless I update.
Okay, so then we say dump save of mmset object dash dot mx Okay.
I'm putting it again outside of data.
I'm sorry?
You're putting you're saving it outside of data again.
Oh shoot. Absolutely incompetent.
Dump save is like lighter for some reason.
Well, maybe. Okay, so here, first of all, why don't I get rid of the WXF file?
Okay.
Unless it's got, but when I have the graph, I'm going to use
Property. Well, computing graph from the object is pretty quick.
Okay, but then I'm going to get, okay, so let's say Metamath graph there, and I want to just store the graph. Okay, so I'm going to say export data slash set dash graph dot wxf Metamath graph
dot.
Okay. 10 megabytes in an instant, saved in an instant. Okay, now what do I want to do here? Now I want to take, you're saying I now want to make that distance matrix, right?
Right.
Which I have to make from the dependency graph.
Yes. Well, it's the same code. You already have it.
Yeah. Okay, meanwhile, let me clean this up. That's irrelevant. Okay. Okay, so now what we're going to do here. What are we trying to do for that plot? Remind me what that was again. The plot, how does that relate? Oh, for goodness sake.
We're trying to bundle some of the theorems.
Yeah.
Use that.
And get the other color.
The same approach.
No, I understand. But what's the F rows doing? We're trying to just count theorems, right?
I think it's F rows is basically the size of the vertex out component for each of the theorem.
what is this plot again? Remind me what this plot is.
Is the
I thought-
vertex out component size for each theorems, and this is the histogram.
That's why it's
Okay.
written how many reachable theorems from a given theorem are there.
Like your first column is
Yes,
basically
I understand. I get it.
maximum.
I get it. Right. So the zero thing is the axioms.
That's right.
Close
And
to
these
zero.
are small lemmos.
Yeah.
Okay. Do we have an interpretation of this picture? So I think the picture wants to be the bottom should be logic, then set theory, then these other things. Right? It's layering.
Well, the interpretation you wanted to understand this little peak here around 4,000.
Yes, I did.
You wanted to know what kind of theorems they were, and now you have the breakdown. Now
Okay.
you can
Let me
see.
just save this. Let me save this. So we're going to save this in a dump save or a, what do we think? A WXF file or dump
Good
save?
first to check the byte count of it, and maybe try to reduce it somehow, because I think it's too big. Oh gosh.
Well, we did succeed in saving it before. Maybe we shouldn't bother to save it.
Maybe
Well,
you should save the F rows instead.
what is F rows? F rows, but I mean, F rows is the amount. How many reachable theorems? Okay, so that's per theorem. How is its out component? How big is its out component, correct?
Yeah. Maybe like, doesn't matter.
What?
Instead of accept infinity, blank integer would probably work faster.
Oh, who knows? Okay, so then, okay, so this thing here is what? Is the biggest, what is that?
Yeah, it's like the thing with the largest out component.
Yeah. Wow.
What is it, Dirith? Can we look it up?
Sure.
Sounds Jewish there.
Dirichlet's theorem.
Which is what?
There are infinitely many primes in any arithmetic progression, coprime to n.
Wow.
It's interesting.
Well, I think I should mention that that's the winner. Let's look at the last few, probably.
Yeah.
Just check, see whether they're all number theory. Was this really the most efficient way to do this? Why didn't we just look at just vertex out component size, the length of the vertex out component within the graph? Why did we make the distance matrix? What do we need the distance matrix for?
I know the idea was that it's like in one swoop, you can compute the size of the vertex outcome instead of like mapping over.
All right, okay, so let's save this. Let's do export set data / set dash out component sizes. Okay, .wxf. I wish we had in here. You know what? I want to put this in an association. This isn't an association. I want to put in an association with the names, with the vertex list names. You get what I'm saying?
Okay.
Does that make sense to you?
Yeah. Association thread vertex list F rows. Vertex list Metamath graph. Comma F rows.
Okay. Isn't it amazing how fast that goes if it isn't like multiple gigabytes? Okay, so now, for example, here we just say take largest by outsizes. Well, actually, just take largest of outsizes, comma 5. Okay, what are these other things? And why is this much smaller? This is 10,000. Why is that much smaller than your 25,000? Do you see what I'm saying?
That's what Deershey was before.
Oh, that was the position.
Yeah, that was position.
Oh, phew. Okay. Good.
Oh yeah, there's the size. Okay, all right, okay. So this is
log sum. What is that? Let's see. The sum of log p over primes. It's, well, I'm not sure that's a terribly exciting one. What else do we have here?
okay, all right.
Another number theory one.
Could you give me a link? Could you put a link in the chat to the Metamath page for this?
Yeah, sure.
Okay, all right. Now we're going to make this plot. Okay, so this plot here. Okay, that was what I had for that, which is really straightforward. But we can read this in. And this would simply be histogram of values of outsizes, you know. Okay, there we go. Same graph. Now you've managed to make a better graph that has IC. And that's better too. Okay, so you've got, okay, why did you, okay. So we want stacked bars, but
We want fewer.
Well, why did this go up to 4,000? This goes up to 8,000. Oh, the different bar sizes.
No, it's because, Nick, it's because we removed the miscellaneous ones, right?
Yes.
So
Supplementary.
a significant number of these are under the miscellaneous category. This
Okay.
is something else that we found.
Okay, fine. Okay. So here, where's theorem fields?
Theorem fields, it's the same as Metamath sock. Just yes, the same thing.
Okay. So why don't I just say Metamath sock? And what's this? That's Metamath graph. Okay, so let's say length of bar data. 21, really?
It's how many bars. Oh, it's how many. Oh, it's just.
Okay, so this is for those. But where's the 1,000? That doesn't look right. I don't think we should do this with bars. I think we should do this as a histogram. I mean, how do you do a stacked histogram?
I have no idea. You can. I'm not aware. You can do it. I'm not sure.
We had a version of this that was in terms of percentages. Right, Nick?
No, it's just an option. Yeah, it's just a layout option. Don't think you can do a stacked histogram.
You can do stacked histogram. It's part of chart layout.
No, it's just it's when you actually manually do it.
There it is. Accumulate the data.
Yeah, exactly.
Multiple displays of data, stacked. Okay, so let's look at what stacked would look like in. So all we want to do is we want to distinguish by, by where it's from, right? For each thing in
right.
outsizes, okay, we want to take these and, okay, so where did we get this list from? Where do we get that's Metamath sock, right?
Yeah, you just came up your Metamath sock on this.
What will that do?
That will.
No, because if you key map this onto
Okay.
that, you'll get a bunch of colliding things.
Right.
So what we want to do is we want to gather by which of these the keys are in, don't we? Look, here, we want to gather up all those keys, then we just look up all those keys. That's the thing we want to do. We want to invert Metamath sock. Am I making sense?
Yes, yes.
Is there an easy way to do that?
There's some function, pretty sure. Something like association key. Oh, hold on.
Okay.
Maybe even transpose.
look, I can just do normal of this thing. I mean, here, I mean, are you finding something, or is it? Otherwise, I can just do
You
this.
can just group by your Metamath sock identity keys.
Okay, tell me how to do that.
Just group by, like
By.
that.
Beautiful. Okay. All right. Fine. So for each of those, okay, terrific. So for each of these, we will then map outsizes onto that element. Okay. And for each of these, we'll then, well, okay, well, let's just do this first. So we'll say outsizes /@ hash ampersand /@ this. Do you agree?
Oh yeah. Delete missing.
Okay. Now, what we want to do here is probably say histogram of that, and where does stack chart layout? Okay, magnificent. Okay, now all we have to do is figure out how to combine some of these things.
That's right.
Okay.
Mhm.
So let's decide what we're combining, and then we'll probably have to write that differently in the group by. Well, actually, we can change Metamath a sock, right, to do that.
Yeah, exactly. Well, some of these
Okay.
groupings are not that hard.
Okay, well, hold on. Okay, let's first of all get all of those out. So what is that? That's the right-hand sides of Metamath a sock, is it not? Union of values of Metamath a sock, correct?
Correct.
Actually, let's do delete duplicates. I don't know why that's a useful idea, but we might as well. Okay, there we
There
go.
you go.
Okay, now we want to get, for each of these, we want to say hash arrow placeholder, this, and let's just, for good measure, let's put this whole thing in a column. Okay. So classical first order logic, let's just say logic here,
Yes, I agree.
with with lowercase l or a
Fine.
capital L. What do we do for the other post? Let's see.
Lowercase.
And the other post.
In Euclid.
Yeah.
Okay. Set theory. This we're going to call none. Okay, this we're going to combine and call it set theory, as well.
Mhm.
We're not going to distinguish those. I'm going to
Set
call this
theory.
set theory.
Number.
Real and complex numbers. Okay, so I would say, let's just say numbers.
Yeah, right.
Number theory. How many of those are there? Let's find out.
400.
Let's have it be called basic structures.
Okay.
Category theory.
Yes.
How many are there in order theory? Oh, there are a lot. Tons in basic algebraic structures.
Algebra. Oh, can we just say algebra?
That's reasonable, yeah.
Analysis.
Yep. Functional analysis there.
Mm-hmm. Geometry.
Which is tiny.
None. Yep.
Okay.
Mm-hmm.
Okay, so now we want to apply this to Metamath a sock. Right?
So.
Okay. And now we want to say we want to delete the ones that are none here. How do we do that? We get rid of the key that is none. How do we say that?
Key drop.
Key dot.
Yeah. Okay.
You need to change the. Oh, you don't. Oh, no, never mind. Yeah. Okay.
Why are there so many colors here?
Well, we still have quite a few different areas. We only really grouped a few of them, like set theory and numbers.
Maybe legend. Other legend.
What should we say? Chart legend?
Chart legends. Thematic. That percent.
See, there's still quite a few of them.
Maybe numbers and number theory.
Well, that's the thing, right? Do you want to group them like algebra / linear algebra, numbers?
Well, what are we
number
going to do?
theory?
What are we going to do in the original thing? Well, let's just look at how big some of these are. Okay, set theory, the full set theory is big. Okay, so we've got logic, set theory.
Order theory is pretty small. It's only 294.
Oh, I misread that. Okay.
Geometry and category theory, not that big.
That green one is numbers, right? Well,
Yes.
let's try a new grouping here.
Okay.
Where, okay, let's turn that into numbers. Let's turn basic structures into set theory. Or we could do that with order theory as well. Let's
Do you know what exactly the basic structures are? Do you know what they are?
I think that there are things where you're doing structural operations. Let's
Cool.
group functional analysis and analysis together.
What about algebra and linear algebra?
Definitely. Okay, I think we should put basic structures. I'm going to claim, let's try this, basic structures. Okay, topology, geometry,
Yeah.
graph theory, which basic, should we put, let's put graph theory and basic structures.
Can we do, geometry / topology?
Yeah, geometry and topology.
Yeah, okay. This should be better.
Something,
same
oh,
thing.
percent.
Yeah.
Okay, let's reorder those bars. How do we do that? We simply say this association how do we do this? How do you reorder an association?
Just give it a list with the order you want.
Okay, so we want set theory. I think logic, numbers.
Isn't logic supposed to be before set theory?
What's that?
I think logic is supposed to be before.
I know, but you see it's going to look bad because of that bar. See what I'm saying?
Oh, okay. Okay.
I think we should put basic structures here. Yeah, I don't think that works. I think we have to do map this over that. What? As we map this over that. Oh, for goodness sake. We do an association map of this over that. Is that right?
Maybe you should use part, right? If you use part with association in a list, I think it works.
Okay, there we go. Okay, what's the green one? Basic structures?
Yeah.
Let's combine that into set theory.
Okay.
Maybe algebra, because it's like
You're right, that's better. Why do we still have basic structures though? Because we did this. That's pretty reasonable. That's a pretty reasonable picture.
Yeah, I think it can be interpreted now. Now, what's
Let's
interesting
insert
is
this. Okay, hold on. This is frame arrow true. Aspect ratio arrow half. Okay, so let's do this. Let's insert this here. And let's say and now we want to do the outsize thing. Where do we get the outsize from? Outsize is we exported to this. Okay, theorem distribution is here. Okay, there might be some details of this, but that's basically going to be reasonable. We want probably chart label styles changed and stuff like this. Okay, but now up here,
now, yes, okay.
we're going to want to do the same thing, I think. Okay, do you know if there's a chart legend styles?
There's no chart style. Oh, sorry. No, I get it.
Okay, well, I'm going to just make a note here. Make legend names smaller. There's got to be a way to do that.
Do you want to label x-axis?
I guess we could. What would the label be?
I don't know. Dependency size.
Oh, it would be proof size, I think. We're calling it proof size.
Oh, if it's clear from the text, then yeah. It's like expanded proof. Unrolled.
It's, you know what? It's going to get too complicated if we.
You usually
It's just
don't
gonna-
label these. I mean,
Yeah.
it would stand out if you did that.
Yeah, I don't see a reason to label it.
We can just describe it. Now, why don't we answer the question that we sought out to answer in the first place, right? Which is, it's interesting. So there is this bump here, and you wanted to know why there was one. Well, basically, it's numbers in algebra, but those numbers are somewhat large in the next bin there too. But I think it's the only instance where you have quite a few from both algebra and number theory.
No, but I don't think so. I think what's happening is there's a theorem in number theory or numbers that you have to get to that theorem. You get what I'm saying?
Yeah.
Before you can get through there. I suspect it goes through that theorem.
Right. So the
which are
the floodgate has been opened. I got it. You can, now that you have that one, you can entail many more that are of somewhat comparable. Yes, that could be. Yeah, right.
Okay.
But the point is that it's for those areas, most likely. Well, yeah. Well,
comes from, I mean, we should find out what the theorems are. I mean, something is happening down there at 1,000. I mean, we could just find out, isn't this what the dominator thing in the, this is a graph, right? So we need the dominator graph or something of this, if I'm not mistaken.
I don't know.
It's what most of them go through to get below.
There was some kind of new function quite recently about it.
Yes, dominator graph. Now, I mean, this one here, we will need to color. Presumably, we color it the same way as this, or we have, but we certainly can't have yellow there. Possibly recolor, although there aren't very many theorems here, so I don't think we should. Okay, all right, what's next? I mean, we'd like to find out what that is around there, what the number theory.
Well, shouldn't we just do that now?
What does it depend on, right? What does it depend on here? That is, if we select, let's select a bunch of number theory things and let's find out what let's just select the out components of a bunch of number theory ones, okay?
Okay.
Okay, so now what we want to do, and by the way, we may yet want to use the full list that we made here for the original Pythagorean thing. Do you get what I'm saying? We should generate that original Pythagorean graph. Can we do that right now? This graph here. See what I'm saying?
Yeah. Okay.
So that's simply the vertex out component.
Yeah.
If I'm not mistaken. Vertex, is it the vertex out component? Yeah, it's the vertex out component graph of pith G and Metamath graph, right? Pith G, Pythag. And then what I want to do here, then we need to well, it's going to be a reverse graph of this. And then it's going to be graph layout, arrow, spring electrical embedding. And then for this,
why spring electrical? Is it where?
Oh, I didn't mean that. I meant that graph. Okay, now we want to have the vertex labels, vertex style, arrow. How did these get made? That's some particular color map. So let's figure out. I don't know. Let's pick your favorite. Let's just do a random color one map for now. We'll say vertex style hash goes to color data 97, let's say, of, okay, hold on. What we want to do is for each of these, we want to look up. Do you get what I'm saying? We want to look up which of these things it lies in, right?
Right.
Yeah.
So let's do it for the final list that we've made here. Okay. So now it is in a sock. So it is Metamath a sock of hash, right? That gives what that thing is. And then we say slash dot, put those things in there. Okay, then it's this thing slash dot mappings. And then
Some color scheme.
it's this first position in this of that first to first position slash dot vertex list of G. Something's gone wrong here. That has an extra bracket.
Okay.
You know what, before we do this case, oh God, let me just, oh no, don't tell me we just crashed. We just crashed. Well, let's be glad that the Metamath graph was easy to recover. And where's Metamath a sock?
Metamath sock, some kind of cloud get. Maybe you should save it too.
Okay, let's do Metamath graph. I'm not sure that this is how we want to do them anyway, the Metamath graph. Oh, come on. That's because we didn't do. Okay, this isn't the right way to do it. I mean, this isn't the right way to do it. We should put these in cloud objects.
Wait, is it? It's the wrong directory. You have to.
Oh yeah, yeah. Right.
Draft file is a different one, different place.
Why is that taking so long? That's really weird. Wasn't that big? It's 10 megabytes. How can it take any significant time?
Maybe it's doing something in memory then.
Like constructing the graph.
I don't know, maybe there's some kind of data structure that it's for that is encoding it into. I don't know. Huh. Something's not right.
Okay, this thing is very dead. I think this thing is an absurdly large. I'm going to kill everything. Okay. Since we lost the kernel anyway.
Yeah, right.
This is really weird. This is really weird. That's crazy shit.
No, why is it so slow? Come on.
Well, it's not only slow, it's also spinning.
Maybe we saved it somehow incorrectly. We tried.
Okay, how do we get this Metamath thing? Let's get this. Let's save it as an MX file. How do we recover it again?
Or what if you import that setMem object with all the definitions? Does this work?
I mean, we can try this. I don't remember what those the that was just brought in by setMem object. What the hell? That's the thing without that definition, right?
It wasn't a dump save.
No, that was a dump save. That thing was a dump save, but the graph was not. Okay, but the important thing here, let me copy this, because this we claim that's this. Okay, so we need the Metamath graph, and then we need Metamath sock. But where were those previously? Do you understand my question? I mean, we had the, what's that?
Somewhere in the block, the draft of all Metamath sock, I think it's already there. It's just a cloud get command from somewhere.
It is. But this is the wrong Metamath graph. So isn't it the wrong Metamath sock as well?
No,
Surely it is.
I haven't reproduced it yet, but I think it's just a crawled Metamath site.
Yeah, I understand, but wouldn't it be the
So,
wrong size? If the Metamath graph was wrong, wouldn't the Metamath sock be wrong as well?
Or maybe just not all the vertices there. That's why we had delete missing.
I see. Okay, so you need to get that right. But this is clearly wrong, right? This cloud get is now wrong.
The graph, yeah, that's outdated one.
Right. So what should we do here? I mean, I can leave this here for now. I should go fairly soon. And tomorrow afternoon, we have a live stream set up, but we can make it a non-live, working session, if that makes sense.
Yeah, I understand, because we're mostly working on very particular formatting issues.
Yeah,
might not be appealing to a larger audience.
No, I don't.
Yeah, I agree. Great. Yes.
Okay, so hold on.
Yeah.
Let's
go back to what we were doing before, right?
Yeah, are we going to go back to this? Are we going to try and solve this right now or not? Let's try and solve this right now. If you can get Metamath graph, but I'm pretty sure Metamath sock is wrong. See what I'm saying?
Wrong. It is wrong just because it's missing some of the vertices.
Yeah.
Right. Exactly. Yeah.
I think it's still enough to get like the big picture.
Yeah, it is, but but it's wrong. So we don't want to
we don't want to include something that's wrong, right? Can we fix it now, Nick? Do you think
the Metamath sock?
Yes.
Yeah.
Not really, because I have no idea how it was crawled from the Metamath side.
Steve and Nick, I don't mind working with Nick for maybe an hour or so, so even after you go to bed.
Okay, all right.
We
Okay,
can we
fine.
can deal with it then.
Look, we can go on for another 15 minutes or so right now.
So let's
with
find
me.
something that we can do.
Okay, so
within
let's
that
go
time.
through the other things that we know we need here. Okay, I mean, there's a bunch of formatting stuff here. We don't need anything there. I mean, this is detailed formatting stuff, which I'm not going to
So
go
let's
through.
identify what other obstacles are there, to your continued writing, right? That's
Okay,
the key.
so hold
focus.
on. Okay. The final statement of the Pythagorean theorem with all definitions resolved is an expression of size blah.
Don't we think it's like size 6, Nick? We have an answer for that.
Size what?
Depends how you count it.
Well, the same way that we're counting the ones for Euclid up here, which is we just need the number of theorems, the total number of copies, like this thing here, right? We need a correct version of this.
Yeah.
Right.
We have
and
that.
then that, do we have this?
Yeah, Nick, we have this. We did this last
Well,
night.
this is the size of the vertex out component, right? That f rows, whatever we had, out sizes for the pythag.
Yeah, and we made these last night. We have these graphs.
No, it's not the size of the vertex out component. No, it's not. No, look at this graph. This graph is much bigger than that because this graph unrolls. The vertex out component has shared things. This is a tree, right? You wrote a piece of code, right, that unrolls that tree, unrolls the DAG into a tree.
Yeah, but just in the case of the Metamath, it's unfeasible to actually unroll. I had this dependency count thing, right?
No, don't actually unroll it. We're not trying to actually unroll it. We just want to know the size.
Yeah, it's the giant size, like 10 to the 20 something.
Yeah, I know. So that's what we want to know for the Pythagorean theorem. That's what we want to know. We want to know that number.
Yeah, well.
Okay, and so then here, see this thing here? We want to integrate these numbers into this table.
Yeah, I know that. I know. But that's not a key. You don't need that to start writing.
No, I don't think so.
No. So we haven't done it yet. We're just trying to do everything.
Okay, well, I think these are what we need, and I've got these. Okay, is this picture close enough?
Well, we showed you there was another version of this that's cleaner.
I know, which I didn't like very much. I mean,
so what don't you like about? I mean, the colors.
Okay, hold on. Here's it. Okay, I thought it was not showing the right thing. I mean, I think. Okay, what's this make the overlap picture?
It's between Pythag and Pythag. Oh,
no,
sorry. That's not right. Hold on. Let me go back
Okay,
to my
what this is the picture that shows of the famous theorems, how much overlap do they have? Okay, so theorem against theorem, you see what I'm saying? Theorem against theorem, how much do they overlap? So some theorems will show, I was thinking we just make an array plot.
Right, I remember this. This is the pairwise intersections between the nodes of the out components.
Yes.
Yes, I remember this. That's fine.
Okay.
But do you need this to keep writing?
Look, I don't have that much more to write. Okay, I don't have that much more to write. So it's...
No, but look, Stephen, 2 nights ago, you basically said, I can't continue writing.
I know I can't.
Obstacles are overcome.
I can't.
Right.
I can't.
So we're trying to resolve
okay,
those obstacles.
Let's go through this then. Okay.
Yes.
Okay. I kind of need this because I'm either going to talk about it or I'm not. Okay. So let's look at the end. Okay.
Yeah. Good.
Okay. Okay, so this picture here,
Yes.
we probably want that picture there
Yes.
is
Yes.
basically this picture here.
Yeah, but it's stacked, right?
Right, it's just this picture separated. Okay, so let's see what that picture looks like. Oh, God. Yeah, I mean, let's look at that picture separately and see whether it's at all interesting, because that's just this picture. Right, it's the exact same picture, but it's not stacked.
That's right.
Okay, and we may end up with this picture without segregating them here, but stacking them separately down here. Okay, so the only other thing was, is there anything that can be said about the Metamath graph overall, like its dimension or anything like that? Or its branch shield graph? That's the other thing.
Okay. Okay.
Is how does its branch shield graph? This is the dependency graph. So, in fact, this is basically a coarsened branch shield graph. You know what? Maybe I don't need a branch shield graph, because this is basically the coarsened branch shield graph, because this is showing dependency between areas, right? And I like the number of areas here, so we'll need to have, you know, again, for that other plot, I don't even know whether we want to build the stack that way, or whether we want to have another, you get what I'm saying.
Yes. This should match. Probably, right?
Maybe, or we can aggregate some things. But this is about the right number of elements here. This is a nice picture.
Good. Okay. But this section above, there are some details to be filled in here. Is there anything that surely we can help with this?
Which
This
section above?
Well, this look, no, go back down, go back down. This is sparse right here. There's X's, all of this.
Yeah, no. What is the global structure of all named theorems? Okay, the issue there is, what can be said about the global Metamath graph beyond what we're already saying? Like for Euclid, the full graph is this thing here.
Yeah.
Okay, now for Metamath, it's clearly much bigger.
Right.
Now, one possibility, okay, the Metamath graph has 40,000 theorems, right?
Yeah.
I wonder whether we can do graph layout on that number, even if we can't draw the graph. Because if we could draw something which looks like this and just shows the positions of all of those vertices. See what I'm saying?
No, not exactly. Not exactly.
Get rid of the edges, but leave the graph. Get rid of the edges. Get rid of the edges, but you're doing graph embedding and you're just laying down vertex positions without having any edges.
So there'll just be a mist of vertices.
Yeah, with color coding.
With color coding. That's interesting. Okay.
I don't know if that can be done. I mean, the thing that I'd like to be able to do, so here, we see this layout in this metamathematical space.
Sure.
Which we don't see. How could we lay out the Metamath graph in something like this kind of thing? In some approximation to this branch hill graph.
Maybe just graph embedding works.
No, wait a second. Could we generate the branch hill graph? We can generate the branch hill graph from the Metamath graph, can't we?
That's, I doubt it.
Why, you think it's too big, Nick?
No, it's just, yeah, okay. All right, okay. So then what can we do that is a proxy? Well, we've got the graph distance matrix, right? Could we not? Well, we can clearly take a random sample of all points and lay those out. Am I confused with the graph distance matrix? You can lay them out with some, how would you lay them out? With some dimension reduction thing or something? Does that work?
For example,
What's that?
on, I don't know, you just use the usual layout, but you only care about positions of vertices. So you
No,
can have the
I understand, but I'm saying that I don't think. Okay. The question is, we got 40,000 vertices, right?
Mhm.
And 100,000 edges. Okay, so the question now is, okay, one thing we can do is measure the uniformity. That we could do. Right, we've got, I think I did that. I think I was doing that in some other thing. You look at the distribution. Yeah, I tried to do that. You look at the distribution of sizes of yeah, I tried to do that in one of these files.
I mean, dimension measurements.
Well, yeah, dimensional geodesic ball size measurements.
Yeah, I think we were doing it during the stream. Even.
Okay, so which one was that?
No, this isn't it.
This is definitions, I think.
Won't it just be that? Oh, no.
I don't know which one it is. Oh, maybe it's this. It's this one here, 87. Okay, this was a super confusing set of results. Okay, so hold on. This was. Okay, so we tried to do dimension calculation on Metamath graph. Oh, I see. I did a random sample of the vertices to get this. But notice that one time it was 2, size 2. Oh, I see. Look. Yeah, in fact, we had that other plot. We had that other thing where we looked at the sizes saturating, right?
Yeah.
I don't remember where that was. And we just need to get something which gives us a global sense of what's inside that graph. I mean, what we've got here is the distribution of out component sizes. That's what we've got in that previous picture.
Yeah, look, okay. Nick and I we will continue to think of ways to represent the graph. We can do that.
Okay, all right, okay,
can do
fine.
that
I mean, I
tonight.
think that's the last.
Is that really all you need? I mean, while you're here as a last measure, let's just review. Is there anything else you need?
I don't think so.
Because once we give it, then you can start writing again and we can finish.
I can write again, although there's I really would like to see the somewhat final pictures, because I believe this writing is close enough, okay, that as soon as I have these definition things I can write about. I was going to do the other thing about the implies and NAND and so on. Okay, I can look at that. We could look at that briefly in a live stream tomorrow. Okay, we could just give people a little bit there.
Wait. Do you want to do a live stream or do you want to do a non-live working session? Which one do you want to do?
No, I'm saying there's a little piece that could be done live.
But why do that if that's not the highest priority? Unless you just
because we need to do it. We need to do it. We need to do it. It's a thing for this section. We need to do it.
So what do you want to have a brief live stream?
That's what I want to have, a brief live stream that
okay.
just does the NAND and the implies thing.
And then we'll go unlive and keep working on
yes. I mean, unless we talk a little bit in the live stream about counting the eames, which we might be able to do. Okay, that'll be a fine, publicly interesting thing to do.
That's publicly interesting, but I mean, personally, I would just like to finish this section.
Well, I know. So see how far you can get. And it's going to have a tail. And the thing that I'm worried about is I don't want to write the absolutely final words until we know what these pictures are going to look like.
Sure.
Right? Because, like, for example, we've got, the wrong Metamath graph.
No, I understand.
And for example, even the thing you just did, where you broke it down by category, right? That's not what the writing talked about. See what I'm saying? The writing just expected a picture like this. Now, elsewhere, we expected something broken down by these categories. Okay, so if I'm going to have something broken down by categories, like if this one is broken down by categories, we've got a whole different thing, because then the famous theorems have to be broken down by category as well.
Yes.
So I don't particularly, in this particular case, I don't think this is especially interesting, other than the observation for us. I mean, what I expected is that the shoulder comes from number theory function, things that whatever. I mean, but if we can comment on that, that's great. Then we'll use the data we generated here for something at the very end that goes through and breaks down different fields of math.
Yes, I understand. Okay, but just to look, the comment here has these X's, and you wanted to know, you wanted to.
Yes, but we haven't answered that question. So I mean, if we can answer that, what is there a particular theorem that a lot of things go through?
Right.
Okay.
Yeah.
Which I think is probably what's happening. Then, like for example, for the Boolean algebra stuff. Okay. Everything goes through commutativity. It takes 100 steps, goes through, once you've got commutativity, you can compute a lot of other things easily.
Right. Then the floodgates open. I understand. Right. So we need to find that gate.
Which I think can be done with this dominated graph thing.
Okay. So the point you're making is, okay, here's the thing. I want to be able to discriminate to some extent between, formatting issues that need to be done, that can be done after you resume writing, right? And, generation of the graph, which is really still content generation, where what you write will be contingent upon the results that are shown in that graph. And there's going to be some distinction there, right?
Yes,
I don't want to spend time on formatting and basically saying, okay, Stephen can't write yet because we haven't done this.
Okay, let me tell you. The only thing that I don't think, like this image, I can either comment on it or not, depending on what it looks like. Okay. Okay, this here is asking the whole distribution of human identified theorems, how clumpy and what does it mean? Okay, that's asking the same question over and over again. What is the structure of the Metamath graph?
Yeah.
Okay, and what can we say about that structure?
Now, one difficulty for me is, okay, when there's a cyan comment, it's very clear what to do. you have these comments here that are in the text. And I've usually presumed that that's basically, it's a note that you leave for yourself.
It is mostly,
Right.
it is, but I don't, it needs pre-work to answer it. So what I'm saying is there's a cluster of things here that are all in the same bucket, that are all in the, what can we say about this graph?
Yes.
Okay.
Yeah.
And that's, I mean, because, what kind of conclusion would we like to make? For example, I've claimed above that the theorems in the logic in the Boolean algebra graph tend to be decently, fairly far separated. Okay, the notable theorems in Boolean algebra are somewhat separated in the graph. Okay, that's the claim over here.
Right.
Okay, so the question is that also, so for the Metamath graph, well, I mean, no, we don't even know, because the full Metamath graph includes the proofs as well as, that will be the analog of this graph here. We could make the analog of this graph if we could include the proof structure as well as, you know what I'm saying? As well as the theorem dependency structure. But that may be too hard. See what I'm saying? Because the direct analog of this graph is the proof structure as opposed to the theorem dependency graph.
Yeah.
I think it's probably too hard. Okay, so the
It's not
theorem
about it being hard. It's basically if we can compute it or not.
Yeah, I know. The theorem dependency graph. The question is, what can we learn from the structure of the theorem dependency graph? Other than there's a lot of mixing in mathematics, so to speak. I mean, maybe that's all we can learn at this stage.
Well, let's see. Let's see if we can represent it, and then we can analyze it.
Okay, but then you see, for example, this graph.
Yes.
This graph here is a kind of a cheap branch hill graph.
Yes.
And the question is,
okay, look, what I'm gathering is there are a number of small little issues here throughout this section, but really you're still waiting for big picture results that allow you to speak more confidently about the overall graph.
Yeah, if there's something to say. I mean, there are two levels of graph. There's the graph, the theorem dependency graph, and there's the actual proofs graph. Okay. And I think either one would be, yeah, I'm sorry, I'm getting tired here. Gosh, I am a real creature of habit. It's really literally within a 10-minute period, I get incredibly tired.
Look, it's okay. Nick and I can meet for some time, and then I'm going to go to sleep and wake up, and we're going to do the live stream. So we can work on this, for
okay,
a while.
Fine. But I mean, then I also am keen, just so you know, in terms of flow, right?
Yeah.
Okay, so look, here's what I want to do. There's a little bit more in this section, but I'm fairly confident about this section. Okay. Then I want to go through from the beginning, as we were doing today with that. I want to continue doing that graphic design review.
Yes.
Okay.
Yeah.
Then what I want to do is I want to get essentially to the point where I have finished graphics, or where the graphics are so close to finished that I can absolutely imagine what they're going to look like. Okay. And then I'm going to do a pass through the writing. Okay. And what I do in that pass is I will add links, and I will try and just do whatever remaining editing there is on the writing.
Just let me see if I understand. you're not going to do the final edits and link additions until, if I understand you correctly, most of those cyan comments have been resolved.
Well, I need to know for each picture. Okay. So for example, some of those cyan comments, we were like using the wrong functions and so on to get it. So the graphs will change.
Yeah. Right.
You know what I'm saying? So I don't want a graph. I don't want to be going through.
Yeah,
I
you
want
don't
to
want
go
surprises. I get it. Yeah,
I want to go through and write it because the writing is okay. I suspect that this writing is not perfectly smooth. Okay. I suspect that there are things here where there is some structural stuff that could be changed. I think I'm not going to change it. Okay. So I think that the basic logical flow is decent. I think we're going to cauterize most of the things that have not been covered yet.
Like the gravitation section.
Yes, for example, I think that can perfectly well be cauterized. I think that
by the way, I mean, this is cauterize. This is kind of a metaphor. What does that actually look like? Do you just delete that section?
No, I delete the second half of it. I was going to look, it was actually had reached a reasonable stopping point. And it was just like, it's like one of those conversations you have with somebody where it's basically reached a stopping point and then you restart it type thing. You know what I'm saying? It can be stopped. I mean, it's just like, I'm not going to talk about it. I'm not going to discuss ordinary relativity. I'll change the title of the section and we simply will not have a discussion of ordinary relativity in this piece.
That's fine.
Okay. And, you know, it's for another time. I mean, we're not going to discuss basically the causal invariance business particularly. I don't know whether I've even mentioned causal invariance. I may have done, in which case I've got to look at that. That's the whole point. You see, once I have the whole thing, you know, with everything basically cauterized, then I start at the beginning again and I go through and I make sure that I don't say, and this is all related to causal invariance, which we will discuss later.
Right. I have a feeling you mentioned invariance at some point.
I probably do. So, you know.
Yes.
Then it has to be fixed.
Yeah, you do.
Okay, well, fine. I mean, but then, you know, maybe that's okay. And I just say it's not going to be covered here.
Sure. Good. Okay. Okay. Well.
Okay. Good stuff. All right. I'm going to go, and then I think. I mean, you know, the other things that are plusified are fairly minor.
Yes. Yes, they are.
So yeah.
What?
No, it's fine. It's good. I mean, I'm still agonizing a little bit. If I understood the market for this better, I would consider writing some kind of short summary, but I just don't understand. I don't understand the market well enough.
Did you want to release that, you know, prior to the larger piece?
No.
Well, then who cares? You can wait. Well, okay, you can think about that afterwards.
Yeah, I mean, what I did for the physics project is I released them at the same time. But I think it's probably not necessary because you know, the thing was interesting. I was doing some correspondence this evening, okay? And I found multiple pieces from people who were basically asking about metamathematics with quite long and complicated essays. And I, you know, in some cases I sent them back saying, you know, I'm working on it. We'll let you know later. And some I just stored them up in the mailings thing. But you know, I'm confused here because I think there are people who are definitely interested in this. It's very confusing to me. You know, that there are, I don't know, it's a less, you know, physics is such a well-defined field, and this is not such a well-defined field, other than philosophers of mathematics, of which there are a bunch. of which some of these people who are writing to us are philosophers of mathematics. I just don't
I
know.
have the suspicion that this is going to appeal to a larger community. Because look, we encountered this when we were working on Skolemization. The way that it's usually done is just, it's painful. It's very painful.
No, I realize that. But,
it's
but
very,
I mean,
it's very,
look, I think that there are people who will be interested in this who are more theoretical computer science.
Sure.
But I think it's a, yeah, I just don't know.
But what I don't understand, Stephen, is this, okay, what you're weighing right now, how does that affect the finalization of this?
Doesn't really, except that it affects a little bit. I mean, what I did for the physics project that actually worked fairly well was I wrote this fairly long technical thing.
Oh, okay, yes.
No, the technical thing. And then I wrote much more quickly the announcement because I knew exactly what I wanted to say there. You know, just like here, here's the difficulty, okay? In that case, I understood the compression from the technical piece to the announcement.
Right.
You get what I'm saying? There are plenty of things in the technical piece that I simply didn't mention in the announcement.
Yes.
You know, I wasn't going to talk about, you know, whatever. I mean, different. Now here, there is an argument that there's a whole bunch of stuff about the details of how cumulative systems work and so on that isn't needed. But it might also be that without that, the whole thing is totally frigging incomprehensible to anybody who knows enough to be, you know, able to think about formal things. They'll be like, I just don't understand. I don't understand what
yeah, I understand. I mean, so it's unclear what you should include or could include in a brief introduction.
Because the brief introduction, some part of it is just what's in the first two introductory sections here. Okay, which is fine. That's fine. And people will get that stuff. And then they're like, well, what the heck is this actually talking about? And then they get into the main part. See, I mean, I don't know, things like model theory, right? That you could just cut that out from a basic announcement. Irrelevant, probably, unless somebody is confused and they say, you know, but wait a minute, I thought these things were operators. What is the representation of that operator? And then you're thrown right back into that section again. See, the thing is, okay, one thing I suppose I haven't done, maybe I should think for just 1 second about this is, you know, for the physics project, I understood fairly early how to give an elementary description of what was going on for that project. Okay, you start off with describing the structure of space. You go on and you talk about, you know, how hypergraphs reproduce space. You talk about time. You can then talk about general relativity. Then you go to quantum mechanics, and then you go to Rullial space and so on. It goes. Yes. Okay, here the question is, what the hell do you describe?
That can be done. Look, we examine some advanced aspects of this framework, but thinking about, you know, entailment cones with some simple examples, it's not that difficult. It's not. You could make it simple by just simplifying the framework and including enough that it is accessible. People can understand in a basic way how we're generating mathematics.
Let me tell you why this is hard. Okay, I'll tell you why it's hard.
Yeah.
Okay, only a minority of people read abstract formulas. Okay, formulas this abstract, not only is it not suitable for, I mean, the only people who routinely read these are people who are doing things like ternary writing and combinators and stuff like that. It's a tiny number of people.
So hold on. Does that mean that something like A dot B, for instance, even with that, that's going to be difficult?
Well, what's going to be difficult is when it gets huge.
Yeah, but don't do that.
No.
Why can't we have bite-sized examples that are not?
Okay, we can, but the whole point is that people will look at those things and they'll say, this puffs out into this big complicated thing. Okay.
That's just how it goes.
I
Yeah.
know it's just how it goes, but people look at that and they're like, this is an alien creature. Okay. So something like the hypergraphs in the physics project, because they are ultimately geometrical, people can understand what's going on.
I know. And even when they get complicated, they often become quite, breathtaking. That's the difference.
Right.
Whereas
here, it's just a great
dot
big
B, it's awful. I know.
It's just a great big algebraic formula in a tangled mess of stuff. I mean, the combinator thing, this is okay. For the combinator piece, I didn't write a simplifying combinator piece because I couldn't. It's not a simplifying subject. It's a subject of great obscurity in some sense. I mean, I think I did, I did very admirably to de-obfuscate it, but it's still a subject where you look at those things and you kind of, what you can get from going through that book, for example, is that it's an intuitive sense of what's going on, but it is a very strange kind of intuition. So I mean, look, the big point, which I already make at the beginning of this, is the fact that, there are a bunch of big philosophical points, which I correctly make rather quickly in this piece, if that makes sense.
Yeah.
And then it's like, so what does this mean? And the only thing that one could do probably is jump to things like the empirical mathematics section, except that the empirical mathematics section is very, in the end, equivocal. It's not like, it's not like you run things and there's a smoking gun. You see what I'm saying?
I have a question. Something that I don't understand is, so let's take the hypothetical reader who starts to see these, longer formulae, and they don't like them. Okay. The thing is, you could write an introductory post. Let's say hypothetically you write an introductory post that doesn't repulse that kind of reader. Okay, so they read the introductory post, but they're not going to read this full post. So what exactly are you trying to do? Are you trying to appeal to some reader who ultimately is not going to engage deeply with this, but you still want to find some way of having, some sort of engagement with them? Is that what you want?
Well, that's okay. The question is, and that's why I'm confused here.
Yeah.
Okay.
Yeah. Right.
Okay. Let me explain. In the case of the physics project, the technical thing is intended for people who want to seriously engage. Okay.
Right.
Yet I know that there are a bunch of kind of people who are just generally interested in the philosophy of science, and just the general science, who will be interested in that, but they're not going to engage in the technical details. And it's perfectly okay to get them to the point where they understand, space is discrete, there are these graphs, et cetera, et cetera, et cetera. It's a much less, you're not expecting that they know Einstein's equations. Okay.
Yeah.
The difficulty here is, people have heard of gravity without knowing Einstein's equations. Okay. People have not really heard of, they might vaguely have heard of undecidability and things, but they haven't heard of, I don't know what. I mean,
well, that's it. We have to find the starter kit. I mean, so here's the thing. What do you presume readers know? Axioms? They better. Otherwise, they're going to be lost.
I know that's the point. But listen. There are people who understand the general idea of axioms at the level of Euclid. Okay, they understand that mathematics is a deductive system. Okay, but when you actually show them an axiom and it's A dot B dot A dot whatever, they're like, what the heck is this? I thought the axiom was things like Euclid's fifth postulate. Two parallel lines don't cross. The algebraicization of these things is very alien to people other than theoretical computer science people.
Fine.
See what I'm saying? That's the problem. The problem is,
I get it.
Okay, so I mean, but there's a qualitative.
But is that the same thing with theorems then, as well?
Stating them? Well, I mean, we don't even state any theorems in this whole piece. We do, but only formally.
No. The point is, can we even show something like, one of these token event graphs that appear in this piece quite often? Could we show something like that?
We can show, I can explain look, these are cumulative graphs. It is not difficult to explain the path-based. You've got an axiom. How do you get from here to there? That I can explain. We can do it with strings even. And that's easy to explain.
Right.
Okay.
Yeah.
These accumulative graphs are pretty important if you want to make a connection to traditional A equals B mathematics and to the idea of lemmas building up and so on.
Exactly.
Without that,
that's why I'm asking about them.
It doesn't look much like mathematics. On the other hand, to somebody who is interested in the general philosophy of mathematics, if the question is, was Plato right? Okay. If somebody says, which is the right model of mathematics? Formalistic, Platonic,
axiomatic, constructivist.
Logic based, et cetera. If that's what you're trying to answer, I tried in the first two sections to give an indication of how that works. But I think those first two sections are not bad to give that indication. But the thing that I suspect is that to dive deeper, you have no choice but to understand things about what axiom systems are and so on.
One thing I can say is, 2 points. First is, you have the physics project, right? So if there's something like an axiom, for someone who's, you have the physics project there in order, you can make analogies by comparing this with the physics project. And I would not sell yourself short. I think that there's probably some way to explain what an axiom is in a perfectly accessible way. Even if that person has not thought about axioms before and they were thinking about it in this more qualitative way,
if I'm trying to write a piece that is essentially a philosophy of mathematics piece, okay, that does not get into, which is intended for somebody who is interested in the question, was Plato right? Okay.
Is that the point of this?
I don't know if no, the point of this is that there are physicalized laws of mathematics. It's like Gödel had an arithmetization of metamathematics. This is a physicalization of metamathematics. It explains, that's the whole point. That is the nub of this idea, is it is a physicalization of metamathematics. Okay? Which is absolutely, when people talk about Gödel arithmeticized metamathematics, that is a typical, you are not expected to understand this kind of thing.
Sure.
So I'm saying when people say, Gödel arithmeticized metamathematics, that's in the gobbledygook.
Yeah, but you're kind of presuming they know about Gödel. And if they know something about Gödel, they have some other set of knowledge that you're going to have to presume as well. Because these are going to be related.
Well, yes, they might have read Gödel Escher and got very confused by it. I don't know. It's, because that's a very bizarrely different point of view.
Or they've listened to Roger Penrose explain Gödel on the Joe Rogan Experience or something.
Well, Roger does at least understand it.
No, I'm not saying that's bad, but that was my.
But he will have explained it from a very bizarre point of view.
Yeah, I'm just trying to think of if some person who's not involved in science, they've heard of Gödel, how would they have heard of it?
Oh, in various ways. But they will have heard of self-reference and things, which is just like so trivially not the point. That's the thing. They don't, the idea of Gödel and its relation to computational irreducibility, that's a much better idea. But anyway, look, they're not going to understand. The typical person, I'm reminded of, to give you a sample, okay? There are some Oxford philosophy types who wrote books. The guy who wrote about Frege, who I knew slightly, and who there's a husband and wife team that wrote the sort of standard history of logic book. Okay, it's a good book. But if you look at the level of kind of, they do talk about Gödel in that book. And what they say is not wrong. It's just not deep. If you get what I'm saying. It is superficially correct, but it doesn't really get, as I recall, to the kind of, because I don't think anybody had, I think people like Greg Chaitin have, dug down to the sort of the real significance of Gödel in one way.
Yeah,
I think what we've got in a different way. You know, like I didn't even know until like a month ago that Gödel, you know, one of his motivations was to essentially, you know, prove that axiomatization was a bad idea, prove that Hilbert was wrong.
Mhm.
Now, you know, I don't know. See, this is the problem with physics. Sort of a large class of people are interested. What is at the bottom in physics? You know, what do you get if you drill all the way down in laws of physics? I just don't know what the everyday interest. I mean, people. You know, I'm telling you, you know, like the BBC ran this program that they interviewed me for about, you know, invention versus discovery in mathematics.
Yeah. I know.
I mean, that's a popular question: is mathematics invented or discovered? But I don't know whether that's more than, you know, and obviously we address that here. But
let me make a basic point about framing. Here's the thing.
Yeah.
Let's put this in context. I think that we're now in a different context than you were in when you did the physics project. And here's why. Okay, we have this metamathematics project, and then we intend to undertake and complete a number of other projects that are in various fields. And the question is, each time you do that, do you want to try and
make a technical version?
Hold on. Do you want every single time you do something like this to be thinking about, you know, the pre-existing community, their interest in economics? How do I get those people involved? You can do it. You can do it that way. But I'm viewing this as the first case of what's going to be, you know, a series of projects that pertain to multi-computation. Multi-computation is going to be serialized, right? And so with time, for people who follow this closely, it's going to be obvious, okay, these guys have this new paradigm and they're willing to dig deep each time. And like after a few months, they're going to release something, and they've dug deep into this new topic. And I'm learning more and more about multi-computation, and I'm viewing it through these different lenses. I think that's the better way to sell this than to try and appeal to the specific communities each time, because that's not really the purpose of this. The purpose is to explore multi-computation.
You know what? You know what is amusing? You are precisely making the case for why I spent a decade writing NKS. Because it's exactly the same argument, right? NKS is one paradigmatic idea,
right,
applied to many different things. Okay,
that's right.
Problem is, I can't survive another decade-long project like that.
But we're not doing it the way you did.
I know that. But okay, let me also explain another point here. This is the worst. This metamathematics one is the worst in terms of abstraction, obscurity, whatever else.
Every single one of these after this has both a more, I think it has a larger pre-existing audience, but also has, in many cases, a stronger commercial, industrial, you know, application. This is definitely
no, but this is also look. This is just really abstruse. I mean, all the stuff about, I mean, as we know, mathematical logic is 100 years. You know, there's 100 years of mathematical logic full of scholemizations, right? And when it comes to economics, there's plenty of technical stuff. Okay, the other thing that I want to say about this is, like, for the physics project, we made no serious effort to do the experimental implications in the first instance. Okay, this empirical metamathematics thing is much further along kind of experimental implications than we have tried to do with the physics project yet. And unfortunately, one feature of these experimental, you know, whatevers is they're always messy. You know, this is like data science. It's always, you know, it's kind of partly this conclusion, it's partly that conclusion. It's non-trivial to extract that stuff, and it feels sometimes there's a very, very clear signal. I think there's also high utility in presenting the data in such a way that you even vaguely can appreciate what's going on.
Okay, what's the point? What's the point?
The point here is the other ones are going to be, the other ones will be much more cut and dried. This one, you realize this one is super difficult to write about. It's extremely abstract. it's, it's just going to be, this is not a good, I mean, this one is the high end basically in terms of, and it's also going to be longer. This one is much longer than most of the other ones. I think most of the other ones, my attitude is the first thing we write about them will be basically a plausibility argument. Here's a basic immunological model. Here's how it works. We're not going to get into, whether, the IL-2 pathway is well modeled by this particular kind of, multi-way graph. Right? It'll be kind of, this is roughly how it works. And, I think that's because, I mean, take economics as an example, or any of these things, immunology. It's okay. They're each a little different. I mean, like molecular computing, there's a toy model of molecular computing, and it's actually being done with, alkanes, and it's actually being done with molecules of this shape.
And emerald is actually, involved in, it can become concrete. Yeah,
right. It can become concrete, but the first iteration of this will almost certainly not be like that. The first iteration will be a plausibility argument for this is roughly how it works, probably.
Look, this post and the book, there's a transition from, the physics project, which, okay, from the physics project to this series of projects on multi-computation. Okay, there's a transition afoot here. And I think, one question to answer is, why have we spent so long going so deep into so abstract a project? I mean, personally, it's just been really fun.
Because you
right?
can.
Because we can. Look, we
situation.
can. It's been fun. It's been creative. But there has to be something where it's like, look, on the one hand, it was not that difficult to do because we already had the physics project. And also, the more rarefied this project, the more we get to explore in a nuanced way and in a novel way, multi-computation, because we're trying to explore it in as many ways as possible. So I think part of this is trying to put this in context where you're comparing this to the physics project, and you're also setting this up as some sort of a multi-computational series.
I think you are basically giving me the argument that I needed for the fact that there isn't another piece to write here. This is the piece. And that's fine. Yeah. And I think that if there's a spin-off piece, it will be for some, it'll be a sideshow of this piece. Okay, it'll be something like literally an essay, Plato versus Hilbert type thing. Right? Okay. I mean, not the full story, because the full story, you need to touch most of the issues that are being touched here. I mean, again, the whole point is, let's say take the physics project, and I should go in a second, but the physics project, like, you're going to talk about relativity for the general person. You can explain basic special relativity. You can explain E equals mc squared. You can explain, gravity, and then you're out of there. And maybe you explain black holes. You're not talking about, the details of the energy momentum tensor, because it's just not what people care about. I mean, it's what the professionals care about, but there's no point in mentioning the energy momentum tensor.
I agree.
Whereas here, the distance between the person who understands something like, I don't know, the other problem with this is that almost nothing here is well known to anybody. I mean, much like the combinators piece, there are on the order of 10 people in the world who intrinsically know a bunch of that stuff.
Yeah, but it was a bestseller, at least for some time, on Amazon, right?
Yes.
I mean, it sold well.
It's an interesting, right? Look, it is interesting to people. My point is this, that it can't be the physics project. There are some sort of high points that you can hit, deriving E equals mc squared, things like that, which a person who just knows a bit about physics knows why you would care. In this, that's the real point. For somebody to care I mean, what are the questions that are being answered by this? Questions being answered by this is something about what the intrinsic nature of mathematics is. Okay. And, you know, what people usually say about this is pretty facile. And
it's not just about what the intrinsic nature of mathematics is. I mean, this is something I've kind of tried to emphasize this throughout, and I feel as though
being ignored. What is it?
Yes. Well, it's not that I'm being ignored, but I just feel like more emphasis can be placed on this, which is, you have this piece about multi-computation and about it being a fourth paradigm. And it's a somewhat, substantive piece, but the paradigmatic novelties there are only going to be fleshed out through application to different projects. That's why I've been trying to emphasize things like multi-computational irreducibility and the observer, et cetera, et cetera, et cetera, et cetera, et cetera. So it's not just that this is a new way of looking at math. It's not by coincidence that we've arrived at this way of looking at it. This and the other point here is that, with multi-computation, you're looking at formal systems. So the fact that we've been able to do this with mathematics itself and show its emergence and use these fourth paradigm properties, and the fact that it makes sense and that we feel as though it, it affords us a better perspective. I mean, this is very encouraging. I mean, personally, right? It's very encouraging for this paradigm. This is a great exhibition of the paradigm.
No, I know. The fact that higher level math is possible being equivalent to the fact that space emerges and that they're all based in the Rulliad is fairly spectacular. No question about it. But the thing I just said, that sentence is pretty deeply incomprehensible unless you have a lot. Yeah, anyway, look, it's fine. I think I'm happy with where we're going with this. This is good. I'm happy with it. I don't think I think that any shortened version is going to be basically equivalent to the first two sections here, which is fine.
Okay, but I'll ask you a question, which is, I mean, it's funny with the combinators book, for instance. I mean, so on the one hand, no, sorry, I'm trying to, how do I want to say this? Are you concerned that people aren't going to understand this, basically?
I am concerned. Okay, the combinators book had the following thing going for it. Many people in computer science or theoretical computer science have heard of combinators. They know that they're obscure. That book de-obfuscates what was already known to be obscure.
Right.
Okay?
Yes, I get that.
I mean, it is, combinators are like, as I say in the first sentence, basically, you could do it with combinators, but you wouldn't want to, type thing. That's what everybody knows about combinators. And so this is, you're signing up for something of utter obscurity.
This isn't the same. This project
is not the same. It's not the same. Right, it's not the same. So the question is, what do people come to this project with? Okay, and I think there are perhaps two constituencies. Okay, one constituency, which I think is small, is mathematical logic. No, there may be three constituencies. Okay, there's mathematical logic people. That's the professionals. That's a rather small group. Okay, for whom this will be somewhat alien, but perhaps of great interest, perhaps of no interest. I don't really know. Okay.
Right.
Then there are people who are in theoretical computer science. Some of them don't care about math. So I'm saying the type theory people, for example, it's not obvious that the theoretical computer science part of that cares about math. Okay. I mean, they might say, that's nice, but I don't really care about math. I'm only interested in this for theoretical computer science. If this was relevant to the P equals NP problem, then I care, but it isn't. As it is in fact, but it isn't presented that way. Okay, so that's that constituency. Now that constituency will have no trouble seeing, long sequences of A dot B dot A dot whatever, I think.
Right.
That constituency is used to that kind of thing. Okay. Okay. The third constituency is people interested in the philosophy of mathematics.
Hold on. There are different constituencies. Okay. There's also people who read people who basically follow, Stephen Wolfram writings. And if you post something new, they're going to take a look at it.
Yeah.
And there's some
bunch of those people
there's
will
some
understand this fine.
section of those people who will dig deep and look at it. And all the people who send you mail, for instance, okay, there are those people, right?
So they'll do fine with this.
There are oh God.
Look, I mean, okay. There are those people, they will be just fine. They're people who have read a bunch of stuff I've written, followed what we're doing roughly, or even precisely. They will be fine. If they care, they will be fine to read this. They will have no trouble.
Okay, no, sorry. I wanted to, here's the other thing. I mean, look, I must say on a personal note, whether or not, professors of logic care about this post, I don't care really to a certain extent.
Well, there are not very many of them.
It's not that important to me. It's a very small constituency. I mean, what I care about is, look, there are people who follow your work. There are people who might apply to the summer school. And most importantly, look, there are people who might be, say, Wolfram Institute fellows, might be a part of the Radiological Society, might go to the summer school. Ultimately, if this is going to gain traction, it's going to be because more people read about it, ask us questions, get involved, and start to produce their own research on it. And really, until then, and I know it sounds like this is a commercial for the Institute, but really, until then, this is going to be, somewhat obscure. Now, we have the benefit of, you have a mailing list, you will send it to people. Many people will say, thank you, this looks interesting. They'll kind of, browse through it. Some of them will engage more deeply. That's what I'm guessing you're going to get. You're going to get some engagement.
This is the point. This is the point. This is why this is different from the physics project. Okay, the physics project has two constituencies that are well understood by me. Number one, professional physicists, okay, of which there are many, right? Number two, people who follow physics as kind of just at a general level. Okay, both of those constituencies I understood. I wrote two pieces, one for the professionals, one for the people who follow physics in general.
I get that.
Worked fine.
I totally get it. Yes.
Okay. For mathematics, there is no such similar thing. The people who follow mathematics as a recreation absolutely do not follow this kind of thing. This is not what, for most of them, there are ones who follow the philosophy of mathematics. Okay. There are some very bright, very interesting people who follow the philosophy of mathematics. They will be interested in this. And I want to make sure that they understand this. But I think most of those people won't have trouble with the level of technical stuff that's in here, even though it's totally alien, but it's alien to everybody. So, I mean, see what I'm saying? It's not the case that there's a person, there are popular math. Okay, let's take the Gödel-Escher Bach reader. Okay, I think the typical Gödel-Escher Bach reader will be completely unable to read this.
I agree. Because I know people who read that book who don't know anything about mathematics.
Right.
They came for the Bach, for instst, or the Escher.
Yeah, right. I mean, it's a fun book, but it's not. I mean, similarly, people who read the Raymond Smullyan, Combinators book, that book is, the set of people who, have like the puzzles is not the same as the set of people who like the Combinators book.
Look, I have thought about, this isn't going to happen, but just as an exercise, what if there was an article about this piece in Quantum magazine, for instance? This magazine, Quantum,
yeah, I know.
right?
So
how would they describe it? And I think in part they could try and talk about emergence, and you could maybe say something about the Ruyad that people who read that would understand. But ultimately, at some point, it would basically be made clear that there's quite a bit of new conceptual invention here, new functions, and it looks different from math as people ordinarily understand it. And at that point, people are going to actually read it, because of curiosity and because of their interest in something new.
Yeah, it's a lot of.
That's the way that I've understood the Quanta post. And Quanta is a relatively intelligent community. It's like a Simons Foundation publication kind of thing.
Right. It's done well. It's the new Scientific American.
But that's the kind of readership that
yes,
there is that readership.
I know. And that's hard work for a journalist. I mean, I know there's some things, for example, the physics project, okay, covered by some journalists, but it was hard work for them. This is even much harder work. This is really hard. Good luck to a journalist trying to summarize this.
I think I think there is a simple way, and I hope I'm not too tired to describe it. But look, basically, the idea of simple rules, simple programs, if someone's familiar with you, if they're familiar with NKS, that shouldn't be too hard. Okay. And then the
yeah.
idea that you can start to understand how more rich or more complicated mathematics can be understood to emerge from that. That's not that hard.
Okay.
There's some
The
simple way
first
of
two
describing it.
sections of this are pretty good in describing all that stuff. They're pretty good. They just aren't very ultimately satisfactory because people who this is going to be fine. The main point of this discussion, as far as I'm concerned, the main takeaway is I'm not having FOMO for not writing a second piece.
If that's what this is about, and if that's your takeaway, then fine. It raises other questions that are more complicated that interest me. But if that's the
right,
key,
I think the key thing is there is no obvious second piece to write. Unlike the physics project where there was an obvious second piece to write.
I agree, because there's no, I mean, you wrote that second piece because you knew the audience.
Now, I knew the audience. That
Right,
audience
that's
is the
it.
people who read popular physics books. And, that was a piece aimed at those people. And, it was the people who read popular math books. The closest to this is probably Rudi Rücker's Infinity in the Mind. The closest to being, something where this is in fact, a good sample of this. In fact, maybe the right thing is to see if Rudi is interested in writing something, because he would do a decent job of trying to write something which is a more, a different, look.
This is a good idea, actually.
Yeah, I mean,
getting other people who you think can understand this and who can explain it, showing it to them, maybe getting them to write something. That's a good idea.
I agree. That's a good idea. But and I mean, in fact, Rudi just sent me a bunch of stuff he's written about things of mine. So he understands the stuff well. And he also was a mathematical logic person.
I know Rudi. I know who Rudi is. Yeah.
Right. Okay. But in any case, I mean, one point about this stuff we've been writing is it is whimsifiable, if you understand what I'm saying.
Well, that's what I was trying to suggest with this hypothetical quanta journalist.
Yeah, but they won't get us. It's really hard. I mean, Rudi might be able to do it, but I don't think that the straight shooting,
I'm biased at this point, right? Because I helped make all that. I helped create all this. So it doesn't seem that hard to me. But
but I mean,
maybe you have a better sense of understanding.
I do. And it's hard. This is seriously hard. I mean, I know that like, for example, I gave that talk about consciousness. Okay.
Right.
Which I thought was a good talk.
Right.
I could tell I was 30 minutes in. I was talking to a bunch of philosophers. Okay. Well, the philosophers understood it much better than anybody else. Sure. And, I felt when, I've been talking about the physics project and the structure of space and things like that. And then I felt as I was slipping into the Roolead. Okay.
Yes.
This is slipping to a much higher level of abstraction. And then going back into metamathematics, we are much deeper in the quicksand here. Even though, I mean, because you can't talk about things like space and gravity. You're talking about things much more abstract that people have no intuition for. I mean, the whole point of this post, in some sense, is the statement that the intuition that people have for higher mathematics comes from their intuition for physics. It is the same as their intuition for physics. They're both intuitions about sort of fourth paradigm, treatment of the Roolead.
Right, but the problem is you still have
unbelievably abstract.
Yeah, but the other problem is you just have more people who are who can casually think about physics, just because
it's somewhat concrete.
Because of its cultural status in some ways too. And people could think about axioms more often, but they just don't. You have plenty of people who aren't scientifically, engaged at all, but they still know about gravity. They know about Einstein, like you said. You said, they don't.
I mean,
you can know who Einstein is. You probably don't know who Hilbert or
you wouldn't know who Hilbert was.
Right, exactly.
Right. And you wouldn't know if you asked the person what was in Whitehead and Russell's Principia Mathematica, they would be, I have no idea.
I mean, how much can you say about what's in that book?
Well, fair enough. But I mean, if you said what was Hilbert's program, the number of people who would know that is very small compared to the number who would have some idea what relativity is.
Right. That's the problem. That's why you shouldn't write that other piece.
Yeah,
agree.
I know.
Yeah, I
I
agree.
mean, I think there's special purpose versions of that other piece. If people find I'm telling you, the thing that is to be emphasized, what this is, and the real conceptual advance here, in my view, from the point of view of philosophy of mathematics, is the physicalization of metamathematics. It's a completely unobvious thing. I did not see it coming. It's not something I knew about in NKS. In NKS, I was talking about the computationalization of metamathematics, not the physicalization of metamathematics, if that makes sense. I mean, I knew that metamathematics could be represented computationally, but I didn't make the jump to seeing that it was the same thing as how physics was represented.
Yes. I mean, when I describe this to, like when I start describing this to other people, right? People who have maybe some vague idea of what Wolfram research has done, right? I'm going to emphasize emergence, and I'm going to try and make the case for this idea of a mathematical observer, which is, derived from the idea of a physical observer. I mean, that's it. And, emergence, we don't really use it that much here, but in terms of something that's kind of in the more general lexicon,
I think,
understanding that mathematics kind of
is emergent.
trickles up from basic, computational syntax, and you can actually kind of show how we got what we have today from simple rules, and you can explain, like if you've seen cellular automata, you've seen these other simple rules, you can actually not just study the behavior, but with this better framework that we have, you can actually see how you get things from it. You can see how you can 3D print it from this very basic sense. I mean, that is, people are going to think, well, how the heck do you do that? But there's some way of explaining it using, basic complexity terminology that people
that's
know.
what I've done in the first two sections here. I talk about the emergence from molecular dynamics and so on, which is a good, which that one is handleable. People do understand that. I've discovered people have the idea that one of the most important points there is that people know that fluids like water are made of molecules, yet they also know that they can't tell that from looking at the water.
Right.
And that's an important point. It's kind of like, it's a kind of Copernican type point in some sense. It's like, actually, the Earth goes around the sun, and you kind of know that, but you can't see it immediately. And that's a useful, step up. Anyway, look, this is all, it's all fine. We're on the correct path. It's, it'll all be fine. And I think and I think the buzz phrase is the physicalization of mathematics. That's the thing. As soon as somebody can unpack that buzz phrase, they understand basically what's going on.
But I must say, I understand the reference to Gödel, but in terms of the way that we promote this, I feel as though a buzz phrase that needs to be unpacked has failed to some extent.
No, you see, no. I'll tell you what I think about that. Okay, then I got to go to sleep. I'll tell you, the original name for the NKS book was A Science of Complexity. That was its very earliest name. Okay. Every time I said that name to people, the first thing they said was, that sounds very complicated.
Right.
Okay.
Sure. It sounds complex. Yeah, I get it. Yeah.
Then I changed it to a new kind of science. And the first question people asked is, what's new about it?
And that's exactly the position you want to be in.
Right.
That's what people ask. That's great.
Right.
Yeah. Right.
Okay. So now the point is that in this case, if you try and give this a title that suggests that it's easy to understand, it will not work, because it is not easy to understand. It's actually pretty complicated. And so the idea is to give it something which, has a couple of interesting words that somebody who is sophisticated can see, oh, I can roughly guess what that, I mean, it's very hard to guess what that means. If somebody had said to me, 20 years ago, oh, you're going to write this thing about the physicalization of mathematics, I would have said, what the hell is that?
Well, that's what I mean by unpacking. The fact that they don't know what it is, unless you want them to be
I
attracted
don't
by
want them to know
intrigue.
what it is. I don't want them to know what it is because it's not a thing. It's just like I didn't want them, that's why I called NKS a new kind of science, rather than saying it's the study of programs and this and that and the other.
It seems different. With new, you got intrigue, but you also didn't intimidate people. With physicalization, it sounds like, look, I imagine many people who see this and they think, I like Wolfram's general work. I don't understand physics. That's why I didn't engage with the physics project that much. If this is like that, then I'm not going to understand this either, which is true.
I know. But look, the title of this piece is The Physicalization of Metamathematics and What It Means for the Foundations of Mathematics. So
and then the question is, so what does it mean for the foundations of mathematics?
That's what the piece is all talking about.
That's the point. So they ask that question. That's the question.
And the point is the whole point of that title is the following. Okay. If what you're interested in, if you're interested in the philosophy of mathematics, then what this is telling you is there is a new idea which you do not yet understand that has relevance to the foundations of mathematics. The deadly thing, and the thing I explained this in some note in the NKS book, which I think some people probably mocked, but I'm not sure if they did actually, but it basically said, the first thing you have to do is to understand that there's a big thing to understand. Because as soon as, I watched people when particularly people who are, specialized scientists, I even said this in the preface to the book, that this was going to happen. You watch people and they say, oh, I know all about, spin systems. And I know this must be, you're generating this thing. It must be the renormalization group must explain what's going on. Let me, that's what's going on. Let me, that I understand it. Okay. Then they look at it, they look at it, they look at it, say, what the hell's going on here? I don't understand this. I'm totally confused. And then they just lose it. Right. And so the whole point is, if you tell them there's something non-trivial to understand, you have not seen something like this before, they will not try and understand it with something which isn't going to work. And that's the same thing for this metamathematics thing. If people say, I know all about it, I read Gödel-Escher, I understand self-reference, now this must be about that. It's like, no, it's, you just won't understand it. It's very far away from that.
Right.
So, and similarly, I think people who say, I understand, I don't know what, the formalism of mathematical logic. Mathematical logic is not a popular field right now.
I get it. And look, you did this with the multi-computation post as well, right? Which is, it's a new paradigm. It's just a new paradigm. And, it's funny, people, like when we met with Mario, we were explaining, so this is a new paradigm. And he said, well, wait. Isn't this just like a, non-deterministic automaton or something like that? And it's like, well, there are no observers in that theory, et cetera, et cetera, et cetera. It's obviously not reducible to that, but it's something that people like to do, which I find obnoxious.
It is.
It's really annoying.
I know that, but that's why.
But that's what people do.
One of the important things is you've got to give people. It's it's the same thing for me. If somebody says, let me show you the software product. Let me tell you about this idea, and they just show it to me raw. I will immediately say, I will immediately figure out what's the closest thing I know to this. Okay. If they give me a preamble that says you've never seen something like this before, and they characterize roughly what it is, I have a different approach to it. There are plenty of things where I've been confused because people didn't say that. If they'd said you've never seen something like this before,
right. And you stop trying to make comparisons. You stop trying to find a reference.
Right. And stop trying to, you're not, I'm trying.
No, I get it. Because you basically think, oh, are they trying to do this? Because if they're trying to make it like this, there's this problem. If they're trying to do it like that, then obviously that doesn't work. Right. So instead of doing that.
Okay. For example, there are plenty of things in NFTs, cryptocurrency, those kinds of things where it's like, oh, this is kind of a new thing, but although it's connected to other things, but it is a new thing. It's not something where it's just like, it's just a such and such. I don't know. I mean, you know, like I don't know what, you know, some
I kind of have
DeFi
that. I'm
exchange.
starting to have that opinion at this point, but yes, a few months ago, I remember that feeling. Yes.
Right.
Right.
Okay. I gotta go to sleep. Talk to you guys soon.
Okay.
Okay.
See you tomorrow.
Thanks. Okay.
Thanks.
Bye, guys.
Bye.
Good night. Yeah.
Bye.
Oh yeah. Hmm.
Recording. Still recording. It's funny.
No, I guess that big sigh was just recorded. No problem.